Okay, so thanks everybody for joining us today, and I think we're very excited to have Mac Schwager from Stanford with us today. He directs the Multi-Robot System Labs and is at Stanford. He got his bachelor's from Stanford and master's and PhD from MIT, and was a postdoc at the University of Pennsylvania and MIT, and was at Boston University as an assistant professor from 2012 to 2015, and has received several best papers. And today he's going to talk to us about enabling robots to cooperate and compete. So I'm very excited to have him with us today, and we'll have a virtual clap. And then just from a logistics perspective, if you have questions, please post them in the chat, and we'll try to pick them up and then ask them. I think that will make it a little easier in terms of the interaction. Okay, thank you.
All right, great. Thanks a lot, Sebastian. Thanks for the kind introduction. So yeah, it's a pleasure to be here. Thanks for the invitation. And I wish I could come in person. I was saying earlier, I've never been in person to CMU, but it's kind of a robotics pilgrimage site. So I'm sure at some point in my career, I'll be there, and hopefully multiple times. But in lieu of being able to be there in person, I'll have to make do with being there virtually. So as you can see from the title, my interest is in multi-robot systems and in the interactions among multiple robots with one another and robots with people or human actors. And in particular, lately I've been very interested in distributed optimization and the very closely related concept of game theoretic planning. So I'm going to talk about both of these areas in relation to multi-robot systems. So from a high level point of view, distributed optimization is a way to enable multiple robots to work together towards a common goal. So it enables collaboration. And then game theoretic planning is kind of the other side of the coin. It's a way of allowing multiple robots to interact while each has its own individual objective, but still the interaction is in some sense fair or equitable among all the robots. For example, a shared constraint is always obeyed, or no robot gets left with a disproportionately bad outcome. Okay, so I'm going to be talking about these two areas. My talk is divided in half. Let me motivate, firstly, collaboration with distributed optimization. So this is going to be my main sort of motivating application, and I'll come back to it again and again. So the idea is, suppose you've got a autonomous vehicle fleet, like a fleet of taxis, lots of them, 100 or 1,000 or maybe thousands that live all over a city. So I'm going to freeze the video here. So suppose the taxis are in green, right? So maybe we have 50 autonomous taxis, and those taxis are moving around. Not necessarily that they're literally taxis. I'll just say those autonomous cars are moving around. And there are a bunch of other cars, in this case there are 50 in the simulation, that are colored with different colors besides green, that are not participating in this fleet, right? Maybe they're human driven, maybe they're autonomous, but they're not part of the same fleet. So we'll assume that the autonomous car fleet has a vehicle-to-vehicle network. Now this is unusual, right? This is not the current state of the art. Currently, autonomous cars are islands unto themselves. They have all of their own computation and sensing on board. They are not cooperating over a network. So this is thinking, okay, let's do the thought exercise. What if the vehicles do have a network? What if they can share bits with one another? How might they use that network to improve their performance? And so what we've done is we've developed, based on the backbone of distributed optimization, we've developed a multi-target tracking algorithm that's sort of like what you could accomplish with a distributed Kalman filter, but it turns out it's much faster and much higher performance than a Kalman filter. And so let's go back to this video. So that's what's going on here. Is our algorithm works as follows. So say two cars or a small clique of autonomous cars are observing the same target, in this case, that red vehicle. The little dotted lines that link the green vehicles indicate this little clique of their local network. So those vehicles work together, they share some variables with one another, and they co-estimate the location of this other vehicle that's not part of the network. And the key result that I'm going to show is that our algorithm converges a lot faster than state-of-the-art algorithms, which are largely based on the Kalman filter. Okay, so this is to motivate distributed optimization. Let's motivate game theoretic planning and the notion of competition. So competition arises all over the place, especially in applications in autonomous driving, but I think it's most apparent in racing, whether you're racing cars or racing drones. This is kind of the most overt and fun um, instance of competition. So here's a video of human piloted drones. This is called FPV racing. Probably most of you are familiar with this idea. The drones are teleoperated. They have an onboard camera. So you're looking at the video feed from one of these onboard cameras. The pilot is standing off somewhere in another room with goggles on, and they receive this video feed, and they're controlling the drones through an RC unit, right? So fully human piloted. What's amazing here is the speed of perception and the speed of planning. This is miraculous. This is something that humans can do that we're still really struggling to do with artificial means. But what I'm really interested in here is the way the humans compete with one another through their trajectory planning, right? So how does a human decide on a trajectory in order to preserve their advantage in the race, or in order to gain advantage on another drone that's in front of them? And this is the art of racing, right? This is what it means to be a good racer, is that not only do you get around the track quickly, but you know how to defend your position or gain advantage over other cars. And that's the competition I'm interested in. And so this is very much a game theoretic concept. Basically, there's limited real estate there's limited track area that you can navigate on, and you want to choose your path along that track area to benefit you while hurting your opponent. And so I'll be talking about an algorithm that we've developed that's a game theoretic planner. We've implemented this in drones in a little autonomous drone racing competition that you see in this video. The drone with the little green path is using our game theoretic planner, and the drone with the blue path is using a more standard MPC planner. And you can see here that we beat the tar out of the other drone. That's the idea. Now, this was what's called a zero-sum game, which means that my gain is your loss. It's an overt competition. But I'll talk about other methods that we've developed, which are not zero-sum games, which are general-sum games, and those come into play in autonomous driving, where you're not trying to beat the tar out of the other guys on the freeway. So first, let's talk about distributed optimization. So I already talked about this application, right? An autonomous taxi fleet or autonomous car fleet. There's a vehicle-to-vehicle network, and they're trying to track multiple targets. So let's dig into the basics of distributed optimization and build up from there this algorithm for these cars to track multiple targets. So distributed optimization, what I'm talking about specifically is distributed optimization on a graph, which is in itself kind of a strange duck when it comes to the world of parallel and distributed optimization. So what I'm talking about is you have multiple nodes. Each node is associated with a robot, with onboard computation, and with its own onboard available data, right? And what we would like is for these robots to communicate over their network, represented as a graph, to minimize an objective function, which can be expressed as the sum over component objective function. So this is one of the prerequisites for any distributed optimization problem, is that the objective has to be what's called separable, which is that it's expressed as a sum over component objective functions. And in this case, it's very clear the mapping, right? Every component objective function Ji is associated to and available to one robot node I in the graph. And so the kinds of algorithms that I'll be discussing are iterative in nature, as are most optimization algorithms, right? Where each node computes some kind of small scale optimization using its own component of the global objective, and then communicates the resulting decision variables with its neighbors, and then receives that same thing from its neighbors and computes again a small instance of an optimization, and so on. So you keep that in mind, is that the algorithms always have this flavor. So exactly the kind of algorithm I'll be talking about lives in the world of ADMM, alternating direction method of multipliers, and it's specifically built on what's called consensus ADMM, which is a subclass of ADMM algorithms. But it lives within a larger world of distributed optimization, which can be broken more or less into three categories. The biggest, by far dominant category is consensus gradient descent methods. So these are methods that take gradient descent as a backbone optimization method, and then use consensus in order to make them distributed. So basically every agent computes a gradient of a local objective function and then uses a kind of consensus looking term to modify that gradient. It's a huge amount of literature here. Consensus ADMM works in a very different way, and I will get into the details of how it works in a second. But in our studies, we've looked exhaustively at lots of different consensus gradient descent methods applied to robotics kinds of problems versus consensus ADMM. And in our studies, consensus ADMM just dominates. It's just much faster, much more reliable. Parameter tuning is much easier. And then there's a kind of third, say, miscellaneous bucket of algorithms that usually depend on an augmented Lagrangian kind of formulation, and there are lots of different. There's nothing that really ties them together. There's lots of different special cases in this bucket. But I'm going to focus specifically on consensus ADMM. So consensus ADMM is a fairly new algorithm. ADMM, which probably you all have heard of, or maybe you're quite familiar with, goes back to the 70s, alternating direction method of multipliers. It is a distributed optimization technique, but not distributed over a graph in the way that I was describing initially. In fact, it's been known for a long time that it's been kind of an outstanding question of how do you take ADMM and distribute it over a graph, as I described. ADMM typically requires a central node, which has to take messages from all other nodes and compute some kind of central update, and then so it's kind of a hub and spokes model for communication. And it's good for data centers, it's good for cloud computing, but it doesn't make sense for a kind of multi-robot network. Consensus ADMM was introduced in 2010 from Giannakis's group at University of Minnesota. This is a well-known optimization group. And it massages the basic distributed optimization problem in the following way. So you have your separable objective. It's a sum over component objective functions, JI. And the way that consensus ADMM works is it makes a local copy of all the optimization variables, but local to every agent. So now you've just multiplied your dimensionality of your decision variable space by the number of agents. So you've actually made it a lot larger space of decision variables. And then you impose an inequality constraint among all neighbors in the graph that my decision variables at the end of the day have to equal your decision variables. And you can imagine, as long as the graph is connected, this is going to lead to the solution of the original problem, right? So they basically exploded the decision variable space, but then and then made the solution manifold such that all decision variables have to be equal among agents to retrieve the solution of the original problem. And basically you take this formulation, you turn the ADMM crank to generate these two sort of canonical ADMM update steps. And all the ADMM style algorithms have steps like this. In fact, many ADMM algorithms have 3 steps. The kinds I'll be talking about here only have 2 steps. So there's a primal step, which is kind of a small scale version of the original optimization problem that only requires data that's available to each individual robot I. And in particular, that robot is optimizing the augmented Lagrangian that's associated with this consensus ADMM. I'll show you details later, but just suffice it to say, it's its own individual instance that's of this kind of optimization problem. And it's performed entirely by robot I. It's entirely only requires information available to robot I. And then robot I performs what's called a dual ascent step. So here the P variables are the dual variables that impose this equality constraint on the states with neighbors. And you can run through a bunch of math and show that a gradient ascent step on the dual variables reduces to this very simple form. And this requires the decision variables from the neighbors in the neighborhood. So it requires your decision variables, xi, and then also decision variables, xj. So this is where the communication happens. Okay, so great. So this has existed since 2010. We have recently developed an extension of this algorithm, which we call SOVA, Separable Optimization Variable ADMM. And we find that this exploits a structure which is often found in problems relevant to multi-robot systems. And I'll talk a little bit more about exactly what that structure is and why it's evident in multi-robot systems. So here's the idea. With regular consensus ADMM, you have a complete copy of all the decision variables on each robot. And as I said, this makes an explosion in the dimensionality of the space of decision variables. So with separable optimization variable ADMM, what we've proposed is notice that oftentimes these component objective functions, J sub I, only depend on a small subset of the decision variables. So consider this target tracking application that I described at the beginning. You have a car whose position you're trying to track with multiple observing cars. If I'm an observing car and I only see this car for a short time segment throughout its trajectory, those are the only decision variables I care about. And so why do I optimize over all the global trajectory of this target when I've only seen it for a short segment of time? So that's the concept here. The same kind of thing applies for example, a distributed pose graph optimization or a distributed SLAM. If I'm associated with one pose, I don't need to copy the entire pose graph. I only care about maybe my pose and the pose of my immediate one hop neighbors in the pose graph, right? So it's just really a small local neighborhood of all the decision variables. And the key is here that for this to make sense, there ought to be an overlap in these decision variables. So the decision variables on X1 are maybe this fragment of the global decision variables, and on X2 it's this fragment, and there needs to be an overlap. So there needs to be an equality constraint that couples some subset of X1's variables with some subset of X2's variables. So maybe it's just the last element in X1's variables needs to equal the first variable in X2's, the first element in X2's variables. Or maybe it's some arbitrary subset, right? But there's some subset of equality constraints between these. And in fact, in what we've proposed, they don't even have to be equality constraints. They just have to be linearly related through an equality constraint. So it's not that my last element has to equal your first element. It's that there needs to be a linear relationship between my last element and your first element. So this sounds maybe a little abstract at the moment, but in fact, we found that this can lead to just really interesting distributed planning algorithms where this equality constraint basically encodes a dynamics constraint from one time step to another. Okay. But suffice it to say that there's a generality here that that makes this really useful in robotics type problems. And we turn this ADMM crank, we formulate the separable objective in a way analogous to consensus ADMM. We turn the ADMM crank and we end up with these two steps. So we have the primal update, which is, now you can see it in more detail. This is the smaller scale instance of the global objective. So this is performed entirely by robot I, and it only requires robot I's component of the objective. So this would, for example, in the target tracking application, this only depends on the data observed by robot I. And then there's some dual Lagrange multiplier term. PI is the dual variable that enforces constraints between the local problems. And then it's called an augmented Lagrangian rather than just the Lagrangian because you have this quadratic penalty term. So this would, if you're familiar with augmented Lagrangian methods, this would be old news. Okay, so what's interesting here is that everything other than the original component of the objective function is quadratic, right? This is linear and this is quadratic, so altogether this is quadratic. So that means that if your original objective function is itself quadratic, if you're dealing with, for example, a least squares problem, you can solve this in closed form through a matrix inverse. So these primal updates can be potentially very fast. And then the dual update, as I said, you just figure out what is the dual, you can compute this in closed form, what is the gradient of the augmented Lagrangian with respect to the dual variables, and you get this very simple update rule, which depends on the solutions of the primal steps of your neighbors. So you have to communicate those solutions to your neighbors to be able to perform the dual update. So that's the outline of this algorithm that we've proposed called SOVA. So our claim is that when you can take advantage of this, say, breaking up the global decision variables into little fragments among the agents, that you end up with a huge computational speed up. So here's consensus ADMM, which is already a lot faster in our experience than other distributed optimization techniques, compared to our version, which is SOVA, which takes advantage of this separating the optimization variables. And now the speed is going to be very much related to the connectivity of the graph and the number of agents in the graph, right? And so this shows how it scales with the connectivity of the graph. So fully connected, you'd expect to have the fastest performance. And a chain graph, you'd expect to have the slowest performance. This is the most sparse yet still connected graph you can have. And you can see that in both cases, we have our red curve, right, has much faster convergence than vanilla consensus ADMM. In this case, it's maybe 1.5 orders of magnitude faster. For a chain graph, it's a lot faster. In fact, it's hard to even the consensus ADMM, the convergence rate slows down so much that you may be waiting quite a long time for a reasonable convergence. So one could argue that this is 3 orders of magnitude faster here, but probably a lot faster as you go down. And so that's the story, is that you can take advantage of the structure to get a very strong speed up in your convergence rate. And convergence rate is important because what I'm proposing to do here is to solve these optimization problems in an online fashion, either for path planning or for online estimation, state estimation. Right, so you want to solve your optimization problem quickly in your network by communicating, and then you get a new crop of data and you solve your optimization quickly online. Now, how does this scale with respect to the number of agents? And really the question ought to be more posed as, how does this scale with the number of new decision variables that are brought to the problem by new agents? And so what we've done here is we've said, okay, every new agent brings a certain number of new decision variables to the global optimization problem. And now with consensus ADMM, every agent has to add that to its own local copy of the decision variable. So the decision space on every agent is growing every time you add new agents, right? So the decision space for the global problem is growing quadratically, and the decision space for the local problem solved by each individual robot is growing linearly. And you can see that that leads to a bad scaling as the number of agents grows for vanilla consensus ADMM. For SOVA, there's no growth at all. It's actually constant in scaling as you add the number of agents, because every agent brings along its own decision variables, and that's the size of the problem it has to solve. This doesn't increase the size of the problem on the other existing agents. So if you, in this, multi-target tracking application for autonomous driving, imagine you have 10,000 autonomous cars, your Tesla, and you have 10,000 autonomous cars in Pittsburgh or in San Francisco, and they are responsible for tracking 100,000 targets. There's no way you could do this in a centralized optimization. It's just too big a problem. The scaling will kill you. And there's no way you could also do this with consensus ADMM. The scaling will kill you. But there's really a conceivable path to being able to do this online in a scalable fashion with SOVA. Okay, so right, so I talked about SOVA and distributed optimization. Now let's talk about how to make this the backbone for this online distributed target tracking application that I described at the beginning. So this is all work by folks in my lab. This is Ola, Javier, and Trevor. They're all PhD students in my lab. By the way, I should mention that Ola and Trevor were also the brains behind SOVA, which I was just finished talking about. And then also Alex, who's a staff engineer in my lab who specializes in software engineering. So this was also presented in a ICRA paper back in 2020. So I already described the idea. The green cars are working together to track the position of the red car. And in general, there might be multiple red cars that they're tracking. And so let's fill in some details here. So we need a motion model for the car, and we're going to need a sensor model for the observers, for the autonomous cars. And this is going to look a lot like Kalman filtering. But the method that we're going to use to solve this problem is nothing like Kalman filtering. It's based on distributed optimization. So the motion model for the car is you have some nominal motion model, which is represented by x at t plus 1 is equal to f of x, perturbed by Gaussian white noise, right? This is the standard sort of Kalman filter or extended Kalman filter setup. Now, in this ICRA paper, we assume that the dynamics were linear. So it's linear Gaussian, standard sort of Kalman filter style dynamics. But it doesn't have to be that way. Because we're dealing with optimization here, we can deal with a nonlinear f function. But that's, if you go to the ICRA paper, you will not find a nonlinear f function. And same with the sensor model. So the sensor measurements y for every car, y sub I, are related to the underlying target state, x of t, through some nonlinear maps and sensing function g. And in the ICRA paper, we assume this is linear. So it's linear with Gaussian white noise, linear Gaussian sensing model, just like in a Kalman filter. But in general, because this is based on optimization, it doesn't have to be that way. So what are the cars trying to do? At the end of the day, they're trying to do basically what a Kalman filter is trying to do. They're trying to find the map estimate of the target position, the maximum a posteriori estimate. So they're finding the posterior distribution over the target state, and then they're finding the maximum as the most likely given that posterior distribution. And this is given the history of all measurements in time over all cars. So what we're trying to do is retrieve the performance that would be available from a magical oracle sitting with a God's eye view that has all data from all cars accumulated in one central processor. That's what our hope is here. Okay, so maximum a posteriori optimization, great. How do we turn this into distributed optimization? So it's not obvious at all on the surface that this is distributable or separable. It's not obvious that this can be expressed as a sum over component objectives. So it turns out it is. So in the linear Gaussian case, or just in the case with the Gaussian white noise, you can take the log likelihood of this, the negative log likelihood of this is a standard procedure, and then it just turns into a least squares optimization. And in the case of a nonlinear motion model or measurement model, it's a nonlinear least squares optimization. And in the case of a linear motion model or measurement model, it's a linear least squares optimization. So that least squares optimization is separable, and every term that is owned by robot I looks like this. So you imagine the global objective is a sum over these terms, and every component term looks like this. And there are three terms within each of these components. One penalizes modeling, a motion prediction error, right? So the thing that you're trying to optimize now is the current estimate on the state of the target, that's xi time t. And in this case, in our formulation, the one previous time step estimate. So it's kind of a very short, small window smoother. So you're looking at the current time and one time step in the past. Turns out we had to do this in order to preserve this prior information, and I can talk about that more in a minute. But in any case, you have one term that penalizes how far away your estimate is from that predicted from your motion model, how far away your state estimate is from that predicted by your measurement, and then how far your state estimate is from that which you predicted at the previous time step. That's the prior. Notice these are all least squares terms. They're linear least squares terms in the case that f and g are linear functions. And these and they're Mahalanobis distances, right? So there's these are quadratic forms with a matrix stuck in between, where this matrix is associated with the appropriate noise. So the QI matrix is the noise covariance for the process noise, the model noise, and then RI is the noise covariance for the measurement noise. So you take the inverse of these, and these are the information matrices for these things. And then PI is the noise covariance left over from your solution at the previous iteration. So this is the prior covariance matrix from the previous iteration. So this is our objective. We turn this ADMM crank, and we use actually in this case, we could use SOVA or consensus ADMM. So in what's in the ICRA paper, we actually use consensus ADMM, but in more recent work, we've used SOVA to make it more efficient. And every robot now has their objective problem, or their component optimization problems to solve iteratively, right? So there's the primal solve, and then there's the dual update step, which you see here. So now the real question you might have is, great, how does it work in practice? So what I'm showing here is the trajectory. This is the light blue line of one target as estimated by one autonomous car participating in this distributed optimization, okay? And this autonomous car only has data at the points where the trajectory drives inside of this circle. So you see those data as indicated by these rays, right? So you can see it's very sparse data. But still through the distributed optimization, this car is going to be able to estimate very well globally the full trajectory of this target. And then all these other squares are the other autonomous cars that are participating in this cooperative estimation problem. So you can see this is how that trajectory estimate relaxes through iterations of the optimization. And then now I'll show you superimposed this same perspective from all of the autonomous cars that are at the same time estimating this quantity. And you can see the trajectories that they believe are correct start off to be quite different, and then they converge and relax to one common trajectory that's shared by everybody asymptotically. And this is the maximum a posteriori trajectory given the data, all the data in the whole network. Okay, so this is visually how it's working. How well does this algorithm work? And I want to measure this in two ways. Firstly, what's the benefit of cooperation? That's what I'll show you first. So today, as I mentioned, the autonomous cars don't do this. Every car is an island unto itself. It uses only its own data to estimate the other cars on the road, right? And so that's the red line here at the top. And this shows you the minimum mean squared error, or the mean squared error of the, not the minimum mean squared, the mean squared error of the filter. So you averaged overall cars and overall time. So you can see that this is kind of the baseline filter performance that would be expected from today's autonomous cars. This is the benefit of cooperation. This is if the cars cooperate together in order to co-optimize their estimate on where the targets are. You can see there's 3 to 4 orders of magnitude improvement in the mean squared error. There's a dramatic improvement. So clearly, if we can enable our autonomous cars to share data over a vehicle-to-vehicle network, there's a huge benefit to doing that. Now, how about comparison with other existing algorithms? So our algorithm is not the only one out there to do distributed multi-target tracking. There are a lot of algorithms, and many of them, in fact, all the best ones that we're aware of are built on a Kalman filter kind of architecture. So basically you say, okay, if I had one centralized estimator, I would use a Kalman filter to solve for the target position. Great. Now, how do I distribute that Kalman filter? And distributing a Kalman filter goes way back to 2005, Olfati Saber, with the distributed Kalman filter, DKF. We found actually that doesn't work very well for lots of complicated reasons that I won't go into, but there's a much improved version, which we found to be the state of the art in distributed estimation, which is, we call the consensus Kalman filter. The citation is shown there, it's from 2016. And that's what I'm comparing performance against here, is the consensus Kalman filter. Our algorithm, this is our consensus ADMM that's built into the maximum a posteriori target estimation problem. We call this the distributed rolling window tracker, DRWT, because it inherently uses this rolling window over the trajectory horizon of the vehicle that you're tracking. And you can see here that convergence is way faster, orders of magnitude faster compared to the consensus Kalman filter. But convergence is one thing, the quality of the estimate is another. So what's the quality of the estimate? So on this plot, I show the fully centralized, the God's eye view with all data in one processor results computed with a Kalman filter. You cannot do better than this. This is as good as can be done. And that's in the black line. You can see a blue line that's floating just over the top of the black line. That's our filter. That's the distributed rolling window tracker. And I'm plotting two things here. So I'm plotting both the empirical mean squared error, so that's the choppy line, and the dotted line is the trace of the covariance matrix. That's the theoretical mean squared error. So if you average the choppy line, it should line up with the dotted line. You can see that's true for the black and blue lines. It's not true for the red line. So this is consistency. If your filter is consistent, the average of the choppy line should equal the dotted line. So you can see our filter is apparently consistent. And this is important because, okay, we're retrieving performance that's almost as good as the God's eye view centralized case, and we know it. So the we know it is what's our confidence in our estimate, and that's indicated by the trace of the covariance matrix. So if we look at the trace of our covariance matrix, we know that we're doing as well as we're doing. That's important for calibrating our confidence in our prediction, right? Whereas for the consensus Kalman filter, it's not doing very well. That's this choppy line. That's the empirical mean squared error. And it thinks it's doing even worse than it is. That's the dotted line. So it's not very well calibrated on its own confidence. It's quite underconfident, but even so, it's not doing that well. So this is just a case for this filter compared to the state of the art. So why are we not exactly retrieving the state of the art here? Oh, excuse me. Why are we not exactly retrieving the God's eye view centralized filter here? This is a little bit dirty. I'm going to gloss over some details in the interest of time. All the details are in the ICRA paper, so I highly recommend you to take a look at that if you're interested. It has to do with this prior and how we're pulling our result from the previous time step to initialize our result for the current time step. This is all built into this prior error covariance matrix, PI inverse. So, right, so this is what we do is we tie our new decision variable, xi at t minus 1 for the target position at the previous time step, with our old decision variable, which is our target estimate that we computed with the previous set of data, right? And it's tied together through the error covariance. So the lower our error covariance was at the past time step, the more we want to be really close. We want to trust our prior, right? The problem is that in order to exactly get the centralized error covariance step, we would, centralized error covariance from the previous time step, we would have to do another round of communications among our vehicles so that everybody has in hand the same centralized error covariance. And this is slow. This is, I mean, we could do this, but it would slow down the algorithm. It turns out that we pay virtually no penalty, no practical penalty for not doing that. Instead, what we do is every car just takes its own component of the error covariance matrix and just uses it again in the prior for the next optimization round. We can prove that this is actually conservative probabilistically. So we'll always, this is assuming that our error covariance on the prior is no better than it was actually. So it's a provably conservative, but it is a little bit conservative, and we want to quantify how conservative it is, and that's shown in this plot. So basically, if we were to use the true error covariance centralized from the previous time step, we would get this black line for the trace of the centralized error covariance. If we sum up the trace of the inverse error covariance across all vehicles, we get this sum of these colored curves. So where our algorithm is conservative, you can see is this little white gap that apparently occurs occasionally between the black line and the sum of the colored lines. And this plot is also interesting because it shows you how much each vehicle contributes their information to the global estimation task for a target. So you can see here the dark blue vehicle contributes heavily, and then its contribution kind of lags, and then it starts contributing heavily again. You can see over here there's a red vehicle, or several red vehicles that contribute very heavily at the end that were not involved at all in the target estimation at the beginning. And this also highlights an aspect that I've glossed over, which is information handoff. So when one new car enters the network to track, so one new car comes into close proximity of the target and starts participating in this target tracking exercise, then it needs to initialize with some prior. And we have this whole handoff procedure for how that's initialized in a distributed way. And I don't want to get bogged down in those details, but we do this handoff procedure. Okay, so you already saw this simulation. I'm going to show it again because now you can make a little bit better sense of it. The simulation environment is called Carla. This is a recent autonomous driving simulation environment that's built on the Unreal Engine. Many of you are probably aware of this. And you can see now the green cars are the autonomous taxi fleet or the autonomous car fleet. And these dotted lines show when multiple cars are in close enough proximity that they can cooperate to estimate the target position. And here the target position is in red. You already saw that. And you can see the handoff happening here, right? So the identity of the autonomous cars that are working together to track any individual target, that changes over time. And then you can see here again the speed of convergence of our algorithm compared to the consensus Kalman filter. So it's really quite a bit faster. Okay, so this was this consensus ADMM or SOVA style distributed optimization applied to multi-target tracking. So right now in my group, we're in the process of applying this distributed optimization algorithm to lots of other problems in the world of multi-robot collaboration. And I'm going to talk very briefly about a few. So my student Ola has worked lately, has a IROS 2020 paper, just came out a couple of months ago, on using the same SOVA style algorithm, that separable optimization variable algorithm, for distributed manipulation. So the idea is you have multiple robot manipulators, mobile-based manipulators. They're all grasping onto one common object, and they all know where they want to manipulate the object to. So there's some target pose or maybe some target waypoint poses of the object. What they want to do is use a local communication network to optimize their control inputs, their torques and forces that they apply to this object in order to cooperatively manipulate the object. And what's more, there's no global map. So the robots only know locally the location of obstacles. So every robot has some sensing radius with which it can identify an obstacle, and it has to impose a collision avoidance constraint within its own local optimization problem, but without sharing this information to all the other robots. So this robot is the only one who knows about the existence of this obstacle. And what's interesting about our SOVA algorithm is that you can have purely local constraints. So even though this is the only guy who knows about this obstacle, the resulting trajectory plan that everybody agrees on will obey this constraint. So I'm going to go through the details. I'm going to, skip over the details of exactly how we fit the SOVA optimization algorithm into this problem. But I think you can imagine it follows a similar procedure as I've described. And so at the end of the day, every robot is optimizing for its own force and torque trajectory over some horizon and for the pose trajectory of the object, but not the force and torque trajectories of the other robots. Those are entirely hidden from robot I. And robot I is responsible for avoiding collisions with those obstacles that it can sense. And you can see we apply this in a receding horizon fashion. The robots plan over whatever, maybe a 2-second horizon, and then execute for a little while, and then replan and execute for a little while. And this is the resulting behavior. Okay, so just some teasers on some current work. This is work that will be written up in papers that will likely appear in RSS or at least very soon. So we're doing this with planning problems with contact. So suppose we have these 3 blue robots, and their goal is to manipulate this, say, virtual soccer ball along a desired trajectory to end at this yellow square. So the only way they can impose their influence on this ball is by making contact with it. And again, the underlying assumptions are very similar as to this distributed optimization problem before, is that every blue robot is trying to optimize its own action and the trajectory of the quote unquote soccer ball, but is ignorant of the other robots' trajectories. And they co-optimize using this SOVA algorithm. And the same thing here. Same idea, but now we can actually have kind of striking maneuvers. So we can basically induce striking maneuvers based on the underlying objective problem that we're trying to solve. But you can see, by the way, we're imposing contact constraints through complementarity constraints. So if you're familiar with the problem of planning through contact, one of the common ways to do that is to impose complementarity constraints. And that's what we're doing here and then distributing that through the SOVA style architecture. And we're doing this in 3D with full physics. So we have 2 floating robot end effectors. You can imagine these as those are the blue balls. You can imagine these as the end effectors of 2 robot arms, and they cooperatively optimize their trajectory to go down and trap a bowling ball that's falling under the force of gravity, and then stabilize that bowling ball and move it to the target square. And okay, so I talked about cooperative manipulation. We can also do this for cooperative perception. So in this case, I'll talk about pose graph optimization, which is basically the optimization engine behind SLAM, right? Where we have multiple robots. Every robot has its own set of, its own partition of the pose graph, so its own set of poses, and it wants to optimize that set of its own poses cooperatively with the other robots that are also trying to optimize their set of poses, but they want to ultimately find a globally consistent map and set of poses for all the robots. And so we can distribute this with this SOVA style optimization algorithm, and we're fine-tuning this algorithm at the moment, but we're hoping to show that we can solve these large-scale SLAM or pose graph optimization problems much faster than existing centralized techniques, and also in a distributed way that would be amenable to multiple robots going and exploring a building, for example. So you're seeing here kind of a synthetic pose graph, which would, I mean, this is not a building floor plan, obviously, but this is a standard benchmark in pose graph optimization. So you would have to imagine that the robots are driving around the surface of a sphere and then co-optimizing to reconstruct the surface of a sphere. Okay, so this is the first half of my talk. And as always, I've gone a little bit over the first half of my time, but that's okay because actually the second half of the talk is going to borrow on a lot of the same concepts as the first half did. So should I break for any questions at this point?
I think there's one question that just popped up.
Okay.
Could you do a quick comparison of SOVA with DGS style methods, as the dual update looks very similar to the Gauss-Seidel update? And how often are the dual updates communication required in an online setting?
Yeah, so that's a great question. So yeah, there is an entirely separate framework for distributed optimization, which is based on this Gauss-Seidel kind of iterations, which really, strictly speaking, these Gauss-Seidel iterations are meant for distributed solutions of nonlinear systems of equations. So they're not really optimization problems, but you can take KKT conditions and basically solve KKT conditions with Gauss-Seidel updates. So yeah, this is something that we haven't fully explored yet. So specifically within the context of SLAM, there is a previously published result in distributed SLAM using Gauss-Seidel style updates. And we've found in our studies that this ADMM style update structure leads to a much faster convergence and much more reliable convergence. So yeah, I guess that's all I have to say about that. So as far as how frequently we have to perform these updates, it all depends on the application and how much computation you have available. So if you're basically, the more updates you can perform, the more iterates you can perform, the better between subsequent solutions of your optimization problem, right? So if we're talking about this online filtering problem, you get data at time equals t, then the more iterations you can perform in your underlying optimization before the next crop of data comes in, the better. So I don't have numbers on hand for what those update rates were in our application, but I can guess there was something like, something on the order of 100 hertz per iteration for the optimization problem, and something on the order of 10 hertz for the for each, in between each new instance of data, something like that. Okay, so game theoretic planning. Okay, so I motivated this already, right? We want to be able to recreate this kind of intelligent, defensive or competitive behavior that humans are capable of in racing, but we want to do this in a purely artificial way using online planning. So first, let me go through some basic ideas in Nash style games, and in specifically generalized Nash style games. So what exactly is a game? So a game is very closely related to a distributed optimization. So in a distributed optimization, you have a separable objective function, which is a sum over component objectives. The parallel notion in a game is that you have individual objectives. Every robot has its own objective. They're not trying to mutually minimize the sum of those objectives. Each one just has its own objective, and if it were alone in a vacuum, it would be perfectly happy optimizing only that objective. That objective can be a function of its own decision variables, theta I, but it can also be a function of all the other decision variables in the network. So all the other robots, which I'll denote by theta sub minus I. And so in this way, all of these underlying optimization problems are coupled among all the agents. And what makes this a generalized Nash style game is that there's also a constraint which is coupled. And this is exotic in the optimization world, but it's actually fundamental in the robotics world, right? At the end of the day, why do multiple robots have to worry about one another? It's oftentimes because of collisions. And so you want to avoid colliding with one another, and that's a shared constraint, right? So if I want to avoid colliding with you, that depends on both my decision, theta I, and your decision or everybody else's decisions, theta minus I. And so incorporating these constraints make this what's called a generalized Nash style game. And the solution when I talk about a solution, what I mean is a generalized Nash equilibrium. So there are lots of different notions of solutions of games, and I'm focusing specifically on this Nash style solution, which means the following. So a Nash style solution is a set of decision variables, theta star, across all agents, where if I freeze everybody else's decision variables except for mine, then I'm doing as best as I can possibly do. I'm at a minimum conditioned on everybody else's decisions, a local minimum conditioned on everybody else's decisions. Right. So, but this has to be true simultaneously for everybody. So nobody can unilaterally improve its objective. I'm perfectly happy doing what I'm doing, given that everybody else is doing what they're doing. So that's the notion of a generalized Nash equilibrium. So what we're trying to do now is solve for generalized Nash equilibria in the space of trajectories of multiple robots in some sort of competitive or non-cooperative multi-robot scenarios. This could be multiple robots racing in a drone racing scenario, or it could be multiple cars sharing their road on the freeway or merging onto the freeway. It could be a car sharing road space with a pedestrian who's going through a crosswalk. That's the idea. So I'm going to start with an intuitive algorithm that's called iterative best response. And this is a well-known algorithm that's used for game theoretic problems. Maybe not in game theoretic planning, but at least it would be an obvious choice to apply in game theoretic planning. And it's common in regular Nash style games where you don't have constraints. It turns out when you do have constraints, which as I said is fundamental in robotics, it doesn't work. It just doesn't work. We've tried playing with it in all kinds of varieties. It just simply doesn't work. But we have a modification of iterative best response that's called sensitivity enhanced iterative best response. And that does work quite well, especially in zero-sum games. And I'll show you why that is and how it is. So what is iterative best response? The idea is, okay, if you start, so suppose I'm the green drone and I'm playing against the gray drone. So first I assume something dumb for the gray drone, like maybe he stays stationary, and then I plan my optimal trajectory conditioned on that. And then I freeze my trajectory, and I, the green drone, now plan in the place of the gray drone. I hypothesize what would the gray drone do in response. So this is his best response. And then I lock in the gray drone's trajectory and I say, now what should I do in response to that? And that's my best response to his best response. So you see that's the iterative part in the iterative best response. And I keep doing this until I reach a fixed point. Now, it's unknown whether this does reach a fixed point in general, but if it does reach a fixed point, that's great, because that is by definition a Nash equilibrium. So if it does converge, it converges to a Nash equilibrium, which is great. In practice, it doesn't work with constraints. Why does, so in this generalized Nash style game, it doesn't work. Why doesn't it work? So suppose that our only coupling action is through the constraints, and that's the case of in a race, right? The only reason I care about the other cars or the other drones on the racetrack is because I don't want to hit them, right? If I could magically fly through them, I would pretend they aren't there, right? So the only impact they have on my objective function is through the risk of collision. And so if that's the case, right, how would this work? This doesn't make any sense. So imagine the first iterate. I suppose that the gray drone is fixed in place, and then I plan my trajectory, right? Now I've planned my trajectory very optimistically, and the gray drone can do nothing other than move around to avoid hitting me. And then the green drone has no reason to change its action because he's not being hit by the gray drone. So iterative best response converges right away to a completely unreasonable answer if you do this in generalized Nash style games. Okay, so what have we done? We've kind of patched iterative best response with sensitivity enhanced iterative best response. So here's the way to reason about this. So what I want to do is I want to reason about what impact does my current trajectory have on the other guy's optimal trajectory. And that impact is only through the constraints. And so what I do is I take the other guy's optimal trajectory as planned in the previous iteration, and I expand a first order Taylor series expansion on the cost about that previous optimal trajectory. And then that exposes a Lagrange multiplier term that's active whenever the constraints are active. So whenever I'm in close proximity with that other guy, that first order expansion will expose this Lagrange multiplier term, and that's here, right? And so this is the collision avoidance constraint, and this is the Lagrange multiplier. And basically, this is the sensitivity of the other guy's objective function with respect to my with respect to my own decision variables as produced through the collision constraint. And so what do? I take this sensitivity and I directly put it into my own objective for the next planning round. And so what does this do? This means that I say not only is my objective to minimize my own objective, but it's also to maximize his objective. I'm trying to do both at the same time now. I'm both trying to minimize my objective and hurt the other guy at the same time. So this only works for zero-sum games. It only makes sense if minimizing my objective is the same thing as maximizing his objective. If it's not a zero-sum game, if my gain is not your loss, then you're just being really aggressive for no reason. So this really doesn't work for like freeway driving, but it works very well for racing. And so that's the idea. Now we solve this in a receding horizon loop with iterative best response, and it works really well. We can solve it really quickly in 20 milliseconds per online iteration, per online solve within the iterative best response. And it still has the same guarantee, actually. If you reach a fixed point in these iterations, you still are at a Nash equilibrium. That's not to say you will reach a fixed point, but we find that very frequently you do. I mean, overwhelmingly frequently you do obtain a fixed point. And so let's get into a few details. What exactly is the path planning problem within each of these iterations? So you have a racetrack, which you see here. The position of the robot along the racetrack is indicated by the pi k at time iteration k. And the objective is that's SI in this case, is to move as far along the racetrack as possible in the given time. Subject to your own dynamics, we're just going to use very simple first order dynamics here in discrete time. Collision avoidance constraints, this is the coupling that makes it a game, so I can't hit the other guy on the track, and stay on the track constraints, and input constraints. So I have a maximum acceleration that I'm allowed, or a maximum velocity that I'm allowed to apply to the agent. And so this is the thing that I'm solving iteratively online in iterative best response to ultimately converge to a plan, a set of control inputs to apply. And as I said, the coupling between optimizations between one racer and another is just through this collision avoidance. And so this is what you see happening here. The plan that's being optimized for each drone is in green and blue in the video. The green one, as I said, is using game theoretic planning. The blue one is not, it's using just MPC. So in other words, it assumes that the green guy is going to do something very silly, like keep moving in a straight line at a constant velocity, and then moves according to that, or plans according to that hypothesis. And you can see that the game theoretic planner, in fact, I should say here that the green drone has a slightly higher top speed, but starts earlier in the race, right? Starts with a disadvantage, and he is able to overtake the blue drone. If you flip the tables, I don't show the movie here, but if you flip the starting position and the top speed so that the blue drone starts behind, but with a higher top speed, he will not be able to pass the green drone. And so we've actually done this not only in drone racing, but for car racing. So here's scale autonomous cars that are racing in our lab. This is work by my student Ming-Yu Wang. So here we're not planning with first order dynamics, we're planning with the bicycle kinematics that are required to incorporate the non-holonomic nature of the cars. And here, again, the small car has a higher top speed, but starts with a disadvantage, starts later than the bigger car, but it's using this game theoretic planner and it's able to ultimately overtake. And we've also implemented this on a full-scale autonomous car. So this car is called the X1. It's an entirely student-built car that we built at Stanford. It was built under the direction of Chris Gerdes, who's a professor in mechanical engineering at Stanford, somebody that I collaborate with quite a bit. And this is a full-scale car, as you can see. These tests were done at a racetrack out in rural Central California. My two students, Ming-Yu and Zijian, are riding in the car, but they're not driving the car. They're just in there for safety and to monitor the system. The other car is entirely virtual, right? Because we don't want to have full-scale cars driving around and bumping into each other and testing the limits of racing and so on. So we have one full-scale car and then a fully simulated other car. And actually, in this case, we have the flip situation that I mentioned. So our autonomous car has a slower top speed, but starts ahead and is able to defend their position against the faster but less intelligent MPC car. We've also scaled this up to more drones. So this is quite a computationally intensive procedure, but we have multiple tricks to speed up the computation through parallelizing the iterations in the iterative best response. This is described in this Robotics and Autonomous Systems paper that just came out in 2020. And we're able to scale up now to 4 drones, which I showed in the experiment video, and up to 6 drones, which I show here in the simulation, moving in 3D. So previously, the drones I showed previously were, there were only 2 of them, and they were only moving in a 2D plane. They weren't moving vertically. So here we've scaled up through the distributed computation to 6 drones competing and moving in R3. Okay, so we've also worked with our collaborators at, and I'll wrap this up now. So we've worked with our collaborators at Microsoft Research. This is Ashish Kapoor and his team. They've developed a drone simulator called AirSim. Many of you are probably aware of this. We worked with them to develop a special version of AirSim called Game of Drones, or actually they called it, we've called it the Drone Racing Lab. And we use the Drone Racing Lab as a platform to host a competition track at NeurIPS 2019 called the Game of Drones. So in this track, basically we provided researchers with a drone racing virtual environment like this and a nice API, and those drone researchers could use whatever kind of algorithm they wanted to make the drones race against one another. And this was just to promote interest in drone racing as a way of accelerating research in intelligent planning and game theoretic planning. We had researchers, over 100 teams from all over the world, submit entries, and at the end of the day, we invited the top few teams to come in person to the NeurIPS competition in 2019, December 2019. So you can actually download these binaries still and run the Drone Racing Lab and use this as a development environment to develop your own autonomous drone racing algorithms. So we're right at the end of time, so I'm going to have to blow through the next stuff. I'm not going to be able to cover it. It's too bad. This is actually work in collaboration with Zach Manchester, who's there at CMU. And it essentially, in a nutshell, what we've done is develop an entirely new game theoretic planning algorithm, which is applicable to general sum games. So not zero sum games, not only racing, but general, say, highway driving, freeway driving, or in-city driving, where you're trying to share the road with a pedestrian and a bicyclist. And we have a very nice algorithm for solving the same kind of coupled generalized Nash equilibrium trajectories among all the agents. So I'm going to go ahead and stop there and open it up for any questions. Thanks very much for everybody's attention. I'm going to say also thank you to all my co-authors and to my collaborators and to all my funders. And thanks to you for your attention. So I'm happy to take any questions.
Great. Thanks. Thanks, Mac. I'll clap.
Thanks.
For everybody. And yeah, I think we can have questions. You know, you can also try audio questions. If you don't get too many at the same time, if you want to unmute your mic, that's also okay.
I have a question. Thank you for the presentation. In slide 7, how do we know the structure of the graph?
Let's see. Let me teleport back to slide 7. How am I going to do that? I think I have to stop share and then share my share again. There we go. Slide 7, you said?
Yes.
Okay, this one. Can you see that slide?
No.
Oh.
I'm not seeing your screen.
I'm not seeing. What are you seeing? I'm not sure.
I think right now you turn off the sharing.
Oh, I did. Okay, so let me share again. You can see the slide?
Yes.
Great. Okay, cool. So say again, sorry, how does...
how do we know the structure of the graph? Which nodes are connected to each other?
Oh, okay. So we assume that the robots are talking to one another over a mesh network. So they don't need to, they just know it because they know who they're talking to.
Thank you.
Sure. So if you're, yeah, the story is if you're within communication radius of a neighbor, then you know that they're your neighbor, so you can share messages with them.
building on that question,
Yeah.
is the same true for the game theoretic planning case? Like
Yeah.
so in that 4 drone example that you had shown
Yeah.
earlier, um,
Yeah, that's a great point.
so you're saying there's no concept of master or like there's no priority among robots.
There's no
right?
priority among robots. That's right. And let me clarify something that was a little bit obscure, I think. So in distributed optimization, everybody's working toward the same goal. And so it makes sense if they have a communication network, they want to use it, right? And that's exactly what we've done, is leverage the communication network. But in game theoretic planning, it's hard to see why that makes sense. Why exactly would they want to use a communication network? I mean, one could probably cook up some explanations for why they would want to, but at least in racing, you wouldn't want to. Even if you had a communication network, you certainly wouldn't want to tell the other guys what you're planning on doing, right? That would destroy your advantage. Part of your advantage is not talking, right? So there's no communication between robots in any of the racing work that I showed. The idea is that every robot is doing all the computation for itself and the other robots. And this is, you could see this as a way of predicting the trajectories of the other robots. This is an intention inference sort of method. So I am predicting what the other guys will do under the assumption that we all will settle into a Nash equilibrium. And then they're doing the same thing. They're doing the same.
But that also, just to follow up, but that also assumes that other robots allow you to access their state.
Well,
to a certain extent.
I see your point. Yeah. So by states, let's be a little bit careful. So there's the current state of the robot, and then there's the optimization variables. So we don't need to know their optimization variables. That's we're solving internally to predict what their optimization variables might be. That's the intention inference piece. But yes, we do need to know their current state, at least their current position or their current pose. And we assume we can do that with onboard sensing or some onboard estimator. So actually in these drone racing examples, we're doing that. I didn't talk about the perception piece here, but we're actually doing this. So both of the robots have a forward-facing camera, and that camera is visual servoed through the yaw mode of the drone to always look at the other drone. And then they pick up these colored balls. Each drone picks up the colored ball on the other drone and then uses some geometry to back out the relative pose, the full relative pose of it. Not the full relative pose, the relative position of the other drone, not the orientation, just the position.
I guess in general environments, you can do this with features. Yes.
Yeah, that would be the hope. Yeah. In fact, we have another line of work that's more perception focused, where we're not really focused on planning, but actually on tracking the full 6 degree of freedom pose of another robot based on only a monocular image feed.
I see. Okay, that's great. Thank you.
Yeah. All right. Anything else?
Okay, we have one question posted. What happens if you lose observations and are unable to perform a handoff?
Oh, in the multi-target tracking work, I think was the idea. Yeah, okay, so what we do is so let's see. So I'm trying to think of how to phrase this most compactly. So if a target is always observed by at least one autonomous car in the network, then we're good. Then our handoff procedure will maintain the continuity and keep the predicted state of that target flowing from one autonomous car to the next through this handoff procedure. But if there's at some point a target is not viewed by any autonomous vehicle, if there's no measurements on that target by any vehicle, then the autonomous vehicle network stops tracking. It just says all the vehicles that were involved in tracking that target just say, do you see it? I don't see it. None of us see it. Okay, it's not in the world anymore. Forget about it. And then if that car reemerges and is now seen by another subset of the autonomous cars, we just initialize a new filter. There's no history to it in that sense. But the hope is that we'll have a high enough density of autonomous vehicles in the in the cityscape or whatnot that we can keep continuous track of the targets. And there's another kind of frame of mind, which is that if nobody sees that target, we really don't care about it. The only reason we're tracking it is to avoid hitting it, or to better collaborate with it, or to better predict where it's going to go, right? So if nobody sees it, it's kind of irrelevant to the overall goal of the autonomous vehicle fleet, so we can forget about it.
Okay, great. I have a kind of related question. So on the first part, the algorithm we represent SOVA. How that assumes, does that assume complete communication, or what happens if you have dropped messages or something like this?
Oh yeah, that's a great question. So let me go here, right? So the underlying algorithm structure, right, is that you have this communication graph. Everybody updates their primal problem and then updates their dual variables. But before they update the dual variables, they have to share the state of their previous step. So what happens if one of these communication links disappears instantaneously? So there's analytical work on this in the context of consensus ADMM, and then we have done empirical work on this in the context of SOVA, right? So in the analytical work says that basically there's a really strong robustness to communication dropouts. So if you can delay a message, or you can drop a packet, and you know, under certain convexity and bounded delay assumptions, you will still retrieve the globally optimal solution for a convex optimization problem. So there's a specific paper I have in mind that I can, if someone's interested, feel free to ping me by email and I can point you to that paper. It's not by us, it's an optimization theory paper. So yeah, in general, this class of algorithms is very robust to communication delays and dropouts. Now, our specific flavor, the separable optimization variable, we've observed that we also have this robustness, but we don't have any analytical guarantees along those lines. Not yet, we're still working on this.
Okay, great. Yeah, thanks,
Great.
Mark.
Thank you very much.
Thanks for the nice talk, and
Appreciate it.
hopefully we'll see you soon in person.
I hope so too. Hopefully it'll be in the spring or summer. I've been in California for a while. I don't know if my cold weather skills are what they used to be.
That's right.
I'm kidding. I'd be happy to go see the snow any time of year. But yeah, it was a pleasure, and any follow-up questions, please feel free to email me, and I'm happy to also email any pointers to any of the papers that I discussed today.
Great. Thank you.
Thank you.
Thank you. Bye.
Bye.